Hello, hello. Am I audible to an to? Am I audible?
Yes, yes, you are audible.
Okay. I'm waiting for some few other people to join. Then we will start this session.
Sure.
Hello, Ashish.
Yes,
Uh, yeah. Meanwhile, people are joining. Can you introduce yourself? Like we can interact. Uh,
yes. So, I'm Ashish Nandwana and I'm working as a consulting company.
okay.
It's an international consulting company, Donny Group. And I'm project manager over here and I'm having around 16 year of experience. So earlier I have did a course of solar photovoltaic from NPTEL
Okay.
and I'm continuing with another project and I would like to learn about hydrology because I'm having the last project in hydrology.
Okay. Okay. So where is the working location?
I'm working from Gurgaon.
Gurgaon. Okay. Good. Other guy is there. Bala Murugan. Are you here? Bala Murugan? Hello? Bala Murugan? Dhiravia. Dhiravia. I'm waiting for 2 or 3 more minutes, then I will start the discussion. Ashish,
Yes.
can you let me one thing that there should be some credit points will be there for attending this assignment, right?
I have not gone through that one. How much credit
Okay,
point?
okay. Because just I'm just now wondering that why people are not joining right now. I know that there are 2 sessions for the same course. Okay. Okay, we will while like a discussion, we will try to make it more interactive. Okay.
Yes.
Maybe whatever the queries I'm putting, you can reply to them. Okay. Based on your understanding till now, you might have gone through the course lectures uh, from the course instructor, Professor Srija.
Hmm.
Okay, meanwhile, I can introduce myself. So, my name is Prabhat Dwivedi. I'm working as a Prime Minister Research Fellow in the Department of Hydrology, IIT Roorkee. I'm mainly associated in doing research work here. It is related to water quantity and quality both. I think I should start the discussion now. Feel free to raise the query.
Sure.
Okay, please please confirm whether the screen is visible to you or not.
Yeah, it's visible.
Okay. So welcome to the first session, assignment session on engineering hydrology course. So this course is mainly instructed by Professor Srija Pekkat. She is working in the Department of Civil Engineering, IIT Guwahati. Today myself, Prabhat Dwivedi, I am taking a TA class in this course. So what we are going to discuss today is related to water cycle. The discussion will be in terms of whatever you have learned so far from the recorded lectures that you are getting. At the same time, I will be mainly focusing in the tutorial part, like whatever the questions or numericals are there related to literature. Now the second aspect is hydrology. Third is we will be discussing about some questions related to fluid properties. Then there is a residence time concept. We will go through some numerical in this part. Then further coming to the part is Reynold Transport Theorem. This theorem is basically useful for understanding the basic physical phenomena that is taking place when we are discussing about hydrology system. Then at the last we will discuss about what is meant by watershed and what is its significance in the hydrology. So this slide showing the basic hydrological processes which are occurring over a watershed. Please keep in mind that watershed, this word I will be taking more frequently because watershed is just like a hydrologic system. So whatever the processes we are going to study in this course, they all are confined to a specific space as well as the time. So now from the picture, this picture has been taken from Venti Chow book 1988. So this is showing a hydrologic cycle with global annual average water balance. It is basically wait for a minute, I will, okay. Okay, so it is showing that here it is 100 units. So 100 units of precipitation whenever it will be taking on a land, so how it is going to be distributed? So distribution in the sense you can see that there is 100 unit of precipitation which is going to fall over a land. Now we can see that there are certain processes, hydrological processes, that are going to be dominant in the region, that are we can describe in terms of surface runoff. There is some processes where the water is flowing over the land, so we can say it as surface runoff. Part of the water, it may go beneath the surface, so we will call it as infiltration. We can see that there is a process. So this is representing that whatever the water, it is going beneath the surface. This infiltrated water, it can be in form of soil moisture. Like we know that beneath the soil there is a confined porous media is there, which is made of soil solids. Sometimes it also contain liquid that is known as a soil moisture, we can see here, and air is also trapped inside. Further going down, when water is passing or maybe overflowing to the land, it will be taken up by the plants. So here you can see that there are some plants, so water will be taken from these also, and part of this water, it will be accounted in the groundwater flow. Ultimately we can see that out of 100 unit of precipitation, we are getting 38 unit in terms of surface outflow and 1 unit in terms of groundwater outflow. So we can see that in total we have already received 39 units of precipitated water which fallen on the land. Now I want to know, Ashish, can you tell me that how much unit it is going like into the atmosphere?
It's 61%.
Okay, fantastic. There is one more guy I want to know. Is he is getting the things or not? I guess. Let me. Balamurgan, are you here? I I think you are saying, but your voice is not reaching me. You can type if it is possible. Okay. Why your voice is not coming? Like I want to be more comfortable if we are interacting more. Not an issue if it is not working right now. Okay, I'm coming to my presentation again. Ashish, can you tell me once again, is it visible to you? Screen is visible to you?
Yes, yes, it's visible.
Okay, okay. Okay, so you told me that 61 unit is going, which is getting evaporated.
Yes.
So evaporation is one important thing that we have to learn, that evaporation it could be from a land surface and another it could be from the plants also. But when evaporation is taking place from the plants, then we come up with one more hydrological term that is known as a transpiration. Okay, so transpiration is the process that is getting when water is getting evaporated from the leaves. When like in contrast, we can say in combined we can say that if the water is getting evaporated from land as well as the leaves, it is combinedly known as a evapotranspiration. Okay, now one more part of this is like this 39 out of the 39 unit of water that has been disposed into the directly into the sea, we can see we can call it as a ocean. This part is called, we can say, is as an ocean. Okay, so this is an ocean. So here you can see that 420, like we can assume that 424 units is getting evaporated from the ocean. Now what is the distribution of this? So you can see that out of 424 units, 385 is getting precipitated over the ocean itself, and remaining 39 units, it is getting transferred from ocean to land. This is the basic understanding of this. So from this I think you got the basic processes that are influencing in this. These processes are very important in order to model the entire hydrologic system. Now I'm moving ahead. So one more tabular estimate is there. It is also from UNESCO 1978. So what they have done is they have particularly defined the distribution of different water sources. These water sources, it may be in terms of the surface water resources, or maybe subsurface water resources, or maybe an atmospheric water also. Like from the item itself you can see that ocean is there, groundwater is there, soil moisture is there, rivers are there, atmospheric water is there, and as at the last you can see fresh water is also there. Now I want to let you focus on this part, this that is a percentage of total water. Okay, so you can see that ocean it is carrying about 96.5%. Okay. Now other dominating part you can see is that we have 1.7% of water getting stored in the polar ice. So this is a general distribution that is showing and taking place in any watershed. Now this volume part, whatever you are seeing, this volume, okay. Let me my mark. Okay. Okay. Sorry. This. I guess it's over now. Again, it is working. You see. Wait for a minute. There is some
Yes.
problem in this. Let me make it correct. Again, it is why it is happening. I guess if I leave this. Okay. So volume is having another importance in this. When we will be talking about residence time, we will be taking this volume as a input parameter for computing the residence time. I'm moving ahead.
Yes.
I hope you are getting the basic
Yes.
distribution. This is a basic understanding. Now coming to the major part. So in this entire discussion, we will be focusing on questions based on different topics, and simultaneously we will be discussing the basic literature and concepts behind this. So the first question, before going ahead, I want to mention one thing, that firstly, whatever the question you are looking at, you should firstly reply to them, okay, and then based on that we will be going ahead, okay. Okay, so the first question is the science that deals with the study of occurrence, distribution and circulation of water across the earth. So in this picture you can say that earth is like a watershed, and then what are the processes that are going to happen. So we have to count in certain principles. So we will be explaining in terms of science. So can you tell that which option can be correct? There is climatology, then hydraulics is there, hydrology, meteorology.
Yes. Hydrology.
Okay, so hydrology is there, but still, we should know that why, what are the definition, or maybe what is the basic meaning of other terms also. So from the basic phenomena, we can see that hydrology is basically a scientific study representing the movement, then the distribution and the quality of water on the earth and other planets. Now coming to the climatology. So climatology is a scientific study of climate, scientifically defined as a weather condition averaged over a period of time. Now I want to mention one more thing, that when the climatology word comes into picture, you might have come across many problems where people are now focusing and taking a general word like climate change is happening, okay. So why people are just expressing this word climate change? Just because they are considering a large period of time. It may be of 100 years also, 100 years, okay. But if we are talking of small events, like if we want to know that how the atmospheric input parameters, like if we say that precipitation is there, temperature is there, wind speed is there, if we are discussing for a period of one month or maybe 2 months, okay, then we will define it in terms of this meteorology. So meteorology is the branch of atmospheric science that include atmospheric chemistry with a major focus on weather forecasting. So it will forecasting will be done as like if we are having a finer data. Now coming to the last aspect, that is hydrologic engineering. So it consists of an application of fluid mechanics to the water flowing in an isolated environment, and that environment could be an open channel like a river. So in the note I have mentioned that you can see this. Meteorology focuses on a short-term events lasting up to a few weeks. Okay, whereas climatology is basically representing a longer events. Okay, so this is the basic difference is there. Sometimes we get confused with these words, that where we have to use the meteorology, where we have to use the climatology. So this is the basic understanding. Now coming to the next question is that a specific weight of a fluid is defined as. Ashish, can you tell me?
Yeah, let me. Density is equal to volume from unit to density.
Wait a minute. Yes. Ashish?
Is there maybe a third density into escalation due to gravity?
Yeah, fantastic. Good. I guess there is one more option is there. You can see. So this is a basic understanding. You may have gone through maybe lectures. So a specific weight, this is represented by a gamma word. Okay. So gamma is equal to. It is saying that gamma is always a ratio of weight of the fluid per unit volume. Okay. So weight of the fluid is just like we can say we know from the basic physics that W is always equal to mg. So mg divided by v. Okay. So if we take this m and v part together, we will come up with another term that is called what? Can you tell me? It is called
Density.
Yes. Mass density we will say. In terms of okay. So we will say mass density. So it is coming like rho, and now the remaining part will be g. So this is there. So it is saying that weight of the fluid in the first option, you can see this one, weight of the fluid per unit volume. Okay, I guess this one, mass of the fluid per unit volume, this will be a density only, that is the mass density. Then the second option, that is this one, third one, product of density and acceleration due to gravity. Okay, right?
Yeah.
And one more thing is there, last option, a specific weight is useful for hydrostatic pressure application. So right, because there is one principle is there, when the water is moving, so it is causing some kind of pressure. You might have felt when we are taking a dip in the inside the water. Okay, maybe river or maybe a sea. So there is continuous pressure which is building. Okay, this pressure is always having a distribution of rectangle. Okay, and it is always equal to P equal to unit weight, that is unit weight gamma into volume. So this is useful. So what we are doing, we are using this gamma value. Okay, we are using a gamma value here for computing the hydrostatic pressure inside the water when we are going deeper. Like Ashish, have you heard of a recent news that one submarine was just crushed because of
Yes.
the huge pressure was there.
Hmm.
Okay, so this was the reason. So we are using here gamma. Okay, so this gamma is basically representing a one parameter for calculating the hydrostatic pressure. So here first option is clear, then the third option is clear, and the fourth option is clear, right?
Uh-huh.
Okay. So whatever the things we had discussed so far, this is the basic difference, that mass density and the specific weight. What is the basic difference is there? So you can see that mass per unit volume of fluid we will be defining as mass density of fluid. Unit we can see. Okay. I think it is clear, not an issue. Okay. And for the
Yes.
specific weight, we can see that weight per unit volume. And unit is somewhat, you can say it is different. Newton. Can you figure out the Newton? Why is it coming Newton value?
Because gravity is acting. No?
Yes, yes, yes. Right. So gravity is acting there. So it will be combinedly comes under the this. It comes combinedly as a force. Okay. Yeah. Now the next question is, fluid at rest in a state of zero shear stress termed as. Okay. Any idea on this?
1 minute. Related. Yes. No, no idea.
Okay, let me explain that this zero shear stress. Okay, this word is basically explaining that there is net force is equivalent to zero. It is the condition. Okay, so based on the Pascal's law, it has been said that zero shear stress can be found when the water is not moving. If the water is static at a rest, okay, it is not at all moving, then in that case zero shear stress can act into that picture. Okay, so in this regard, third option will be the right one, hydrostatic stress condition. How, we will discuss in the explanation. Okay, so any shear stress applied to a fluid, okay, any shear stress applied to a fluid, okay, no matters how small, will result in the motion of that fluid.
Hmm.
Okay, the fluid moves and deforms continuously as long as the shear stress is applied. But if the fluid is at rest, then definitely there will be a zero shear stress will act. Okay, this is the basic thing. The thing is, if the fluid is not moving, shear stress will be zero. What is shear stress? This stress word we have to note it down, that it is just a ratio of force per unit area. Okay, this is a stress. Okay, and why it is called a shear stress? Shear stress, it is because this force, it is acting tangentially to a fluid or maybe any body which is submerged inside this. Then at that case only shear stress will act. So this force will be a tangential one. Tangential force will act. Okay. The important thing is, when the fluid is at rest, it will account zero stress, shear stress. Otherwise, if there is a little, a small amount of stress have been applied, okay, then definitely there will be some movement on the water or maybe a fluid, any other fluid, like it may be oil also. it may be a water also, anything. Okay. Now coming to the second question, amount of water vapor present in the atmosphere is termed as. This one, amount of water vapor present in the atmosphere is termed as. Any idea?
Yeah, it's humidity.
Yeah, it's a humidity. Fantastic, good one. So it's a humidity, and this humidity is dependent on the temperature. So based on that, it can be divided in absolute humidity as well as the relative humidity. Now there is some facts in based on this, is that this humidity always accounts 4% in the air by volume. Okay. The major sources of humidity is basically it will arise from the in terms of the water vapor only. So 75% it will be contributed from the evaporation. Okay. Now coming to the next question, again, different aspect of water across the earth. This question, are you getting this? Different aspect of water across the earth can be explained with the help of a complex cycle is termed as. I guess there should not be a problem. There should not be any
Water
confusion in
cycle.
this. Yes, water cycle. Good one.
Yeah.
Good one. So water cycle. It should be a water cycle only. Then another question is this. Let me erase this. Okay. Okay, other question is there. Loss of water into the atmosphere through the leaves and the stem of the plant is termed as. We just discussed.
Trans- Transpiration.
Fantastic, good one. Ashish, these are the basic concepts only. Okay, we are just going through the basic concept. Then later stage we will be going into the major questions. Okay, so don't feel that they are very silly. Okay.
No, no, no issue. No issue.
Okay. So surface tension results from the forces, dash forces within the liquid. Have you heard of this surface tension over water surface? Have you heard of?
Yes, I heard
Okay.
it.
Sometimes we have studied in our maybe 10th, 11th or 12th physics. Okay. If water surface is there, sometimes there is a surface tension built based on that principle only. If we are having uh, leaves are there. Okay, leaves can float. It is not getting submerged. At the same time, ant can also like float in the water. It is not getting submerged. So because of this surface tension acting on the over surface, so what is the force that is acting on this surface? It is keeping the things moving. So it is
Yeah.
we can see into the explanation. If you are having answer, you can.
Buoyance.
Which one? What?
Buoyance force, I think.
No, buoyance force is just a action reaction force. Okay, buoyance force is a vertical force. Okay, whenever we are dipping in the water, we are facing a buoyancy force. It is always an upward direction. It will be in vertical direction only against the gravity. But we are talking about the horizontal force. It will be acting in the horizontal surface of the water. So we can see the explanation. This is the explanation for the above two questions. Like there is a water cycle. Okay, first one is a water cycle. Then there is a transpiration process. Okay, and this whatever the water which have been taken by the plants, okay, they are getting evaporated and known as the transpiration process. Now coming to the third question. About the surface tension. So the surface tension of a liquid results from an imbalance intermolecular attractive forces. Okay, this one, imbalance of intermolecular attractive forces. The cohesive force between the molecules. You know about this cohesive force, cohesive and adhesive force.
Cohesive, I know. The force
Okay.
which try to attract the two
Yes,
molecules.
yes, yes, fantastic, good. So this is the basic thing. So we have to keep in focus that intermolecular attraction is basically taking place, and because of this, there is a thick forces which are getting generated on this. This is an interface. Okay, we are talking about this force. So from this particular figure, you can see that there are certain water molecules which are already submerged. Okay, so they are having a net force as a 0, but whatever the water molecules they are at the this interface, they are making a net downward force. Sorry. Ha. So net downward force F. Okay, and because of that only there is surface tension acting on this surface. Got the point or not?
Can you please repeat it?
Okay, just I am basically differentiating the two pictures. Like this one is the first one, you
Mhm.
can see. Okay, this one is first. So here there is a group of water molecule. Water molecules are there. Okay, and now you can see that whatever the forces, like we discussed so far, that definitely there will be some attractive as well as the repulsive forces will be acting on this. So if we say that this particular direction is called attractive force, and then the backward direction force is called repulsive force, then so you can see that for every molecule which are already submerged, they are having a net force as 0. Okay,
Mm.
whatever the, like if we say that there is plus 6 unit of force is acting in this direction. Okay, 6 force is acting in this direction, and the another 6 one is acting in the opposite direction. So it will be getting countered now. So remaining it will be a 0 only. Getting or not?
Yeah, I got it.
Okay, for the second molecule like this one, which is at the this interface, so it is only having if you assume that downward forces are attractive one, so there is a net force is acting in this, because other part in the air there is nothing to basically counter these forces. So because
Mhm.
of this, whatever the molecules which are lying on this interface, they all will be producing a some kind of net force, and that net force will be called as a surface tension.
Hmm.
Okay, good.
Hmm. Got it.
Okay, now the next question is process by which water changes into a water vapor in the hydrosphere is.
Evaporation.
Fantastic. So it will be a evaporation only. Okay, now the next question is density of the fluid is defined as.
Mass per volume.
Good, fantastic. So mass of the fluid per unit volume. So this will be a right answer. You can also see the other options whether they are getting right or wrong. Like first one is wrong. Weight of the fluid per unit volume. Product of mass and the volume of the fluid. Will it be?
Density, no.
No, na.
No.
Good. And product of weight and volume of the fluid.
No. No, no.
Okay, good. So the next question is capillarity results from. Have you heard of this capillarity word?
Yes.
Okay, where you have heard?
Uh, I've studied somewhere. I know these parts.
Fantastic, good. So definitely you might have studied in some kind of water related part in your physics. It may
Yes,
be
in
like in 11th, or maybe like I guess it is in 10th or 11th physics.
10th or 11th
Yeah.
class.
So definitely capillarity.
Anti-gravity, I think it's opposite to gravity. Capillary
Exactly.
action.
Yes. So there is options are there. It is arises from the combination of cohesion and adhesive forces, due to a cohesive force only, due to a adhesive force only, or maybe due to a tension surface tension force.
It's due to surface tension.
Okay, let's see the example. I guess not only the surface tension, there is uh, like there are some other forces are also acting, and because surface tension can't define it properly, because capillarity is basically, from my understanding, capillarity is always like a like water is getting like movement of water, okay, in the negative pressure direction.
Hmm.
I can tell you in some example term, like whenever the plant roots are taking the water now, so they are taking in terms of the capillary only,
Hmm.
and that process basically is taken in terms of a negative pressure. It is called sometimes there is a negative pressure acting on that, and based on that they are carrying the water from soil moisture to their roots or shoots. So you can see the explanation that capillary action is caused
Okay.
by the combination of cohesive forces of the liquid and adhesive forces between the liquid. Why is it there? You can see, you might have well aware of this picture, this one, this column one.
Hmm.
Sometimes we have studied related to mercury as well as the water, why mercury never touches the glass of the tube. You might have answered some of the hotspot questions are there. Sometimes we have gone up with this, okay. So the thing is that there is always a capillary action which is basically associated with the adhesive or might be a cohesive forces. Why adhesive and cohesive? Just because sometimes water is getting it is getting up like it is moving upward, just because of the adhesion is dominating between the particles of water, either water or maybe from the tube particles, okay. But if there is adhesive force is dominating instead of the cohesive force, so definitely there won't be a always a capillary action. So you told na that this surface tension is acting, so yes, T is acting here, but always there is some kind of weight of the fluid acting, okay, and to counter this surface tension, force is acting. So we can't say that only the surface tension force is dominating and it is causing capillary action. No, behind that surface tension, what causing the surface tension as well as the weight of fluid, in order to balance these forces, cohesion, like intermolecular forces. Intermolecular forces, what are the intermolecular forces? They are the cohesive forces as well as the adhesive forces only, okay.
Hmm.
Shall we move ahead? Like,
Yes. Yes.
yeah,
Very good.
okay. Now I guess 1 hour already completed, but if you are not tired, we can continue. Like now
Yeah,
we
comfortable.
okay. I want to know other person.
Sure.
Wait a minute. Okay, he is replying. Sorry, Bala Murugan. Whenever the screen is in a presentable mode, I can't see the messages. Okay, that's fantastic that you are replying. Good to know. Maybe this is the first session, so only two people are here with me. But definitely, uh, as we are going in the detail, like further concepts we are going to touch. we will having more fun, or maybe it will be more interesting to know the concepts. Okay, so I hope in the next week, when we will be meeting, more people will be there. As far as my like I went through the website and I saw only maybe 21 people are enrolled right now. Oh, sorry, they have opted for exam, I guess. So maybe that may be the reason, or maybe another session is going to be there, like after 7. So because of that also. Okay, so I am now continuing. Okay, so the question is like dash taken by a particle of water, okay, to pass through, sorry, my marker is not working right, okay, through a phase of water of the hydrological cycle is known as a residence time. So it is asking about the residence time. It is asking about the residence time.
Yeah, average time.
Okay, that is the average time. Fantastic, good one. So average time is the answer. Let see its description in the detail. So the residence time, TR, is the average duration for the water molecule to pass through a subsystem. Can you define the subsystem of the hydrological cycle? Can you name one of the subsystem of hydrological cycle?
Uh, just like water, surface water, river water, atmosphere.
Yes. So basically subsystem is basically, it is representing a processes. Okay.
Mm.
So what is the basic significance of residence time is that you can tell the time, you will be having an idea of the time, that how much, by how much time the water which is present at the ocean, it is getting evaporated and converted to other like hydrological processes. Like if it is having a surface runoff, once consider a one particle. Okay, if I am saying that there is a sorry, again what is happening, okay, let me focus on this. Okay, so if there is a river, okay, so there is one particle, I am taking this particle as this. So now this whatever the process is dominating in this river, it is called as surface runoff. I am saying it as a surface runoff. So surface runoff, there is a one process. This is a dominating process in the river. Now there is one particle which is present here. Now how much time it will take if the next process, like if I say evaporation is happening. Okay, so this is an evaporation process. So evaporation process is happening. So how much, by how much time this particle will reach up to this particular process, evaporation, like entirely it will change to water vapor. So how much time it will take, it will tell, if we can have understanding from the residence time. Got it? So how it is basically computed, so it is a ratio of volume of the water that is stored divided by the flow rate. Okay, so flow rate, it could be whatever the runoff it is getting finally into the ocean, or maybe a groundwater which is finally getting into the ocean, or maybe flow rate, it will be in terms of precipitation also. Okay, because precipitation can also be taken from ocean as well as the land. Okay, now one more important thing is that we have to note that this residence time will be computed in the units of days or maybe a year also. Okay, now this particular point that is mentioned here, I will discuss, I will come to this point later after attempting one numerical on this. Okay, so
Sure.
this numerical is like this. you have to take your pen on and try to figure out like uh, as per my observation, you might have some kind of like tabular understanding from the lectures. Have you got any kind of table related to residence time or something?
And we don't have any table in that one, but we have one question related to this one.
Okay, so it may be in your assignments, right?
No,
Fantastic.
it's in the lecture. We have one question regarding this one, but we don't have any table regarding the.
Okay,
Uh,
have you been able to get the answer in that?
yes. It's a
Okay,
8.2
fantastic.
days in that one.
8.2 days, fantastic, good one.
Yes.
So 8.2 days. So now we will look at by from the scratch we will look at that how 8.2 days is coming in this. Okay, so the first thing I want to know that what is the formula for computing the residence time.
The volume of water in phase to the average flow rate in that phase.
Yes, fantastic. So storage, whatever the water it is getting stored divided by the flow rate. Okay. So this particular storage term, it will be having in terms of volume, right?
Hmm.
Unit will be in terms of volume, and if we are talking about the flow rate, so we can in general terms, we can take volume in the units of kilometer cube, and for the flow rate, we will take it as uh, area per unit year. We will be taking like this. Wait a minute. Wait a minute. Why it is not? Okay. So kilometer cube divided by year. Sorry. Year. Now, once the kilometer cube will be cancelled out, so definitely we are getting a unit of year.
Mhm.
Okay, so unit will be in year. Now we will firstly look into the tables that how we have to get the value of s. Firstly we have to determine the value of s, then parallelly we have to also look into the values for computing the flow rate. Okay, so now let's see in the next slide. Okay, so this is the two tables are listed here. So from the first table, like this one, firstly you have to figure out that we are focusing on computing the residence time for atmospheric water, right Ashish?
Yes, right.
Fantastic. So can you figure out the value that how much volume, like based on the water balance distribution, as in the earlier slide we have also looked. So based on the UNESCO 1978, this is a table they have provided, and based on that we are taking the value of volume. So you
Hmm.
can see that there is 12,900. It is saying that this is the value. It is getting
Hmm.
stored. Okay. So where it is getting stored? So it is getting stored in the air, right?
Yes.
Atmospheric air is there, na?
Hmm.
So air is carrying this much of amount in the atmosphere. So we are taking this value as 12,900, right? Now
Okay.
come to the next table, this one, and try to figure out the value. We have to know that is a flow rate. So now firstly let me briefly describe that what it is explaining right now. Now you can see, so you can see that precipitation, this precipitation, it is in the unit of volume per year, like it is an like
Hmm.
annual precipitation it is saying. Okay, so annual precipitation in total at the ocean, it is taking place in the units of like this one, like you can say 4,58,000, right? Similarly, on the land, how much unit it is getting over the land, you can see in the values. So which one is having a higher value? Where precipitation is taking place dominantly? Can you say where? Like ocean or land?
Ocean.
Ocean. So ocean always rainfall this precipitation percentage is always high. Can you say the reason for this? Precipitation is always a process that have been severely contributed by an evaporation process. So as
Yes.
we know that ocean is having a larger surface area as compared to the land. Okay,
Mm-hmm.
right? So based on that, evaporation will be dominant in the ocean only, and as soon as the water is getting evaporated, it can easily convert or maybe condensed based on the temperature difference or maybe a pressure difference, air pressure difference. It is getting condensed and it can automatically convert into the precipitation. But always, if you talk about the land, definitely water, evaporated water, it has to be transferred to the land, then only precipitation will be taking place, right?
Mm-hmm.
So during that process, several times what happens, precipitation also get lost also. So we are getting like this much of amount of precipitation annually over the land. Now similarly, you can see that evaporation also, the difference you can see easily. So annually we are having a unit of 505,000, okay, over the ocean, and only 72,000 it is over the land, right? Now one more thing you have to see, that runoff to the ocean. So from the river, every year we are getting a total value of 44,700 from the land only, and it is getting directly into the ocean. Similarly, for the groundwater you can also see, and in cumulative you can see that overall 47,000 something of total runoff is getting directly into the ocean. So you can see that we know that our fresh water is mainly derived from the river groundwater, okay, and now you can see that in total whatever the fresh water we are having, it is getting directly, like we are not capturing sufficiently, okay, to this water, and it is directly getting to the salty water, salty water we can say in terms of ocean. Okay, now we will come for the computing this residence time. So for this atmospheric water, you should know that atmospheric water will be dominated by precipitation process, right? Am I right or wrong?
Mm.
Okay, so the flow, whatever the flow will be like in the atmosphere, it will be dominated by the precipitation. This precipitation could be in the ocean as well as the land. So we have to total add up these values. So in combine, we will get a value of some kind of 5,000. This one, 5,77,000. Something we will be getting a value. This is a value of Q. Okay, and it will be having a unit of something kilometer cube per year. Okay, because we are selecting this value only. You can also select mm per year. It is not a problem. Based on that, you have to see the value of you have to convert the value of volume also, because volume, whatever volume we are taking, it is in unit of kilometer cube. Okay. Okay, so based on this residence time, you can compute that this ratio will come up like 0.022 years, and if you multiply it in 365 days, you will be getting a value of 8.2 days, right? Is it clear to you or not? Like see, you have to whenever the residence time question it will be coming, it could be for any hydrological processes, right? This for this question we are discussing for the atmospheric water, but definitely other question may come up with the groundwater. It may come up like for the rivers. Okay, it can ask for the river also. it can ask for like evaporation, it can ask. Okay, so based on the similar manner, based on like sometimes what happen, these tables may not be available for your computation, so you should have some approximate idea. Okay, that how you can get an approximate idea, like you should be having a volume, like whatever the volume you are having in total, and then based on the percentage of availability of that particular hydrological process, you can convert and you can compute the volume. Okay.
Hmm.
Okay, now we are moving ahead for the next question, that is residence time for surface water is about. Now you have to calculate that. I will provide you the values.
Hmm. Just surface water.
I want to see other person also. Like just now, let me keep. Okay. Okay, 8.2 days. Fantastic. Bella Murugan. Good. Whether I am pronouncing your name correct or not, if not, then really I am sorry for that. Bala Murugan, I guess. Murugan. Okay. Yes, I'm showing you the table here. So can you tell the value of like volume of surface water?
We need to add. I think we need to add this lakes.
No, no, no. Firstly, na surface water. This lake will be contributing very like it will be very little only, right? Wait a minute. Yes, if you are talking about a lake, see. Firstly, you have to see the question that surface water. Okay, so for surface water, you are right. You have to add the lake also. Yes, yes, yes. I was just looking into whether it was a surface runoff process, because in surface runoff then only you have to take the value for river only. Yes, but you are right that we are searching for the surface water only. So you have to add the lakes also. Ashish,
Yes.
I guess it will be surface water. It will be surface runoff only. It will be a surface runoff only. Okay. You have to
Okay.
focus on this surface water as surface runoff, because this particular
And
question,
then we consider only rivers in this,
right,
right?
rivers. Yes, yes, yes. Right, right. Because surface runoff will be dominant in the rivers only.
It's 17 days, I think. 17.3.
Okay, 17.3 days. Okay. So what you are doing?
Uh, Average water flow in that day.
How much volume you have taken? What is the value?
2120.
Which one?
1 minute. Uh, I
Yes.
have taken 2120.
Fantastic. So you have taken 2120, and then like what is the other value you have taken? Q.
44700.
Fantastic. So what is the value you are getting?
So,
Division of that?
so
I-
2120 divided by 44700. I'm getting 0.0474.
Okay, and then multiply
It's
by
in,
365.
yeah, in multiply by 365, we got 17.3.
Okay, fantastic. So we were having options like definitely it is
20
asking,
days.
yes, it will be 20 days approximately. Yes, you are right.
Hmm.
Okay, let me see whether Balamurugan applied or not. Okay, I guess he is still solving. uh, I can ask him answer. Okay, okay, we are moving ahead. Okay, the next question is, now we are just we have completed the basic problems which are basically associated to the residence time in the hydrologic system. Now we are jumping into the Reynolds Transport theorem concept. Okay, so here the first question is the system concept and the control volume analysis are related to form a theorem which can be used for the derivation of conservation principle is known as.
RTT.
Yes, RTD. You have already just I already mentioned. So
Hmm.
what is you have to firstly understand that why we need RTT. RTT is just a fundamental mechanism for modeling the dominating hydrological processes. If we are saying that we are about to model a hydrological processes, then definitely you should think of the point that in every hydrological processes, water molecule, or maybe I can say fluid particles which are there, like if I say water is there, if water is moving, okay, so definitely it will be having a particles. Okay, so definitely whatever the how the particles are behaving, like whether the this particle, it is going to going huh, it is moving along the flow, or it may be getting turbulated. Okay, it is sorry, huh. So turbulence may also be there. Maybe particles are getting rotated, they are not moving ahead. So based on the particles movement, definitely we are just using the fundamental mechanism like this Reynold Transport Theorem, and based on that we will be deriving the basic principles, like I think you have studied the principle like continuity principle. Have you heard of this
Hmm.
continuity
We have
principle?
heard it.
Right, so continuity is one then another one is movement conservation, momentum conservation. There is one principle, momentum conservation. Then another one is energy conservation. Energy conservation. So this particular Reynolds theorem, it is helping us in determining that the this how the continuity equation we are getting, how momentum conservation will be taking place, and how the energy conservation will be taking place when a fluid is moving in any system. Okay, now if we are saying that fluid is moving in a system, so now are you getting the word system? Why we are calling it as a system? Okay, so system refers to a fixed mass with a boundary. Like you can see the picture here, there is a one boundary, you can imagine it as a channel, river channel. Okay, so there is a one boundary. Okay, we are taking a small part of that river segment, and in that boundary we are saying that this particular mass means what? Fluid mass. It fluid mass is getting same, it getting constant every time. Like fluid is not getting lost, we are not having any kind of like what we are saying that liquid is getting evaporated, we are neglecting that. Entire system is basically a constant one. Now the second one is controlled volume. So what the controlled volume is means that we are having a fixed boundary. Like now the boundary is not getting to be changed. It is getting whatever it is there. It will be there for our period of simulation, period of our target. It will be the same only. But we are saying that mass is allowed to cross the boundary. So at the last we can read it like that. This one more thing that I want to add, that there is an alternative name of RTT. It is known as controlled volume theorem. Okay, it may ask from maybe another question. Okay, so this is basically dealing in developing a continuity. Another one is momentum as well as the energy equation. Why we need this? In order to model the distribution of various hydrological processes occurring in the water cycle system. Got it?
Got it.
Okay. Then one more thing I want to add, that movement of fluid in the atmosphere, surface and subsurface water can also be modeled in this. Just I mentioned in the previous diagram that if we are saying that hydrological processes are basically changing, so definitely whatever the fluid particles are there, it is basically getting changed, or maybe it is changing from one location to the other. Maybe in terms in that sense it will be a special one, or maybe with the time it is also changing. So we will be using the word that is called temporal. So if the things are changing with the time, so definitely then a temporal word will come into the picture, and if it is changing with the space, then definitely speciality will be counting in this. Now the next question is related to the Reynold Transport Theorem only. So as you may be knowing that Reynold Transport Theorem, it may have been derived in your lectures. Okay, so you have gone through that. So now the question is asking that second term of Reynold Transport Theorem is related to. Okay, it is the first option.
Second is time rate of change of intensive property to the control surface. Yes. Second
Time
one.
rate of change of extensive property
Intensive.
stored within the control. Yeah, I want to tell you that kindly see the things that it should be divided in terms of like term 1 or term 2. It is written in that sense. Okay.
Second one, I'm telling the option second is correct. I think time rate of change of intensive property to the control surface.
Okay, time rate of change of intensive
Intensive.
property across the control surface. Uh, okay, let's see. Yes, we will see what is the answer for that. Okay, so here okay, you might be knowing this picture. Okay, you may be knowing this picture, right?
Yeah,
That
yeah.
how the fluid mass is transferring with the time. Okay, now RTT, as you know that RTT relates dB by dt. So dB by dt is what? Can you tell?
Time rate of change of intensive property.
It is I
Extensive,
guess it should be
extensive,
extensive
extensive. Sorry,
property.
extensive. It's
Yes,
extensive.
extensive property, right? So it will be a
Yeah.
extensive property to the external causes producing this change. External causes, what could be the external causes? It might be a friction. Okay, surface friction, it might be there. It might be due to the any kind of stress that is happening. So this could be an external cause. Now you can see this particular expression uh, 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 below this one, dB by dt of the entire system. It can be written in terms like it can be written in two terms, term 1 and term 2. Okay, right? Whatever you are saying, that time rate of change, so this whatever the thing like time rate of change, it will be dominated in this way, this term 1. Okay, wait a minute. So this is a term 1. It is representing the time rate of change of extensive property stored within the controlled volume, that is a CV. Now the second term, this one, this is a net outflow of the extensive property across the controlled surface. Okay, why we are saying it as, you can see that B here, you can see B is basically, that is the extensive property at a time t plus delta t, it is getting subtracted by the same property at the time t. So basically the extensive property is same at a one at particular a phenomena, like I can say it is an inflow or maybe an outflow. It could be like among both, it could be either one, because B second this one this extensive property is basically changing by the time, because t plus delta t and then again it is getting t, right? But in this case, like B third, you can see, so what third represent, you can see there, fluid mass occupies at time t plus delta t only. So this is representing an outflow. Are you getting the thing?
Yes.
This is an outflow, but this B1 part is an inflow. This is representing an inflow. So the subtracting the difference of outflow and inflow, it will cause you a net outflow only. So net outflow is changing. That is the thing. Net outflow of the extensive property is changing, and it is changing in the controlled space. It is changing in the controlled space. You might have gone through the derivation of this. So there is one term that is coming there. I'm just reminding you that vector, like v vector dot dA vector. Are you remembering there?
Yes.
Right. So v vector dot dA vector. Okay. So this dA vector is representing that whatever the things are happening, it is in the controlled surface only. It is in the controlled surface. Like I'm just telling you the last part of this particular aspect, vector like dot product of velocity as well as the cross sectional area. This is the coming in the last only. But I'm just correlating with this. Got the point or not?
Yeah, I got it.
Okay, fantastic. Now the next question again comes. It is related to this only, that whenever the Reynold Transport Theorem we are using, and if we are trying to get inflow in negative direction, then what should be the degree? What should be the theta? What should be the theta?
Theta between 90 degree to 270 degree.
Fantastic, good one. But still we have to see the explanation that how it is getting. Okay, Ashish, just what I was just saying you can see here that this is the RTT theorem, entire final RTT theorem, that it is saying that dV by dt in the system, and how the term 1 and term 2 it is showing, right? So this is the term 2, this is a term 2, this is representing a net outflow, and then this is the term 1 that is representing that extensive property is changing with the time. Got it or not?
Got it.
Okay, fantastic. Okay, for your further information, that this dV by dt that we are considering, okay, so it is having a Lagrangian approach kind of approach we have it has been selected in this. Then the Eulerian approach is also counted for in order to capture the controlled volume. So this is there. Now if we are targeting, like if we look into the inflow direction, so firstly we have to look at into this part, V dot dA, how we are describing this. So in the second term you can see this one. Ashish, can you see this?
Yes. V
Okay.
dot dA.
So V dot dA. So you from our basics, like from class 11th or 12th, we know that the dot product will be opened as, whenever the dot product is opening, V into dA into cos theta. We'll take it like this only. Okay. And this, what is the dA? So dA is basically if we are having a kind of fluid in this and it is having a velocity in this direction and it will be also having a cross section, and let's say its cross section is like normal to the cross section, it is having a vector of dA. Whatever the angle theta it is forming here, this theta, it is representing that only. Okay, got it or not?
Yeah.
Okay, so this theta, if you are taking between 90 to 270, it will be coming in the negative direction. Cos theta value will be coming in negative direction. Oh, sorry, it will be coming minus, and because of that, we will be counting a flow, inflow in the opposite direction. It is in the negative direction, right? Now the further question is that the left hand side of Reynold Transport Theorem for the mass conservation principle in the case of single phase flow is?
It's one, I think.
Which one?
One.
See it carefully. Firstly, read. We as from the you can see that RTT is constant. Now what we are deriving here? We are deriving the mass conservation principle. So extensive property. What will be the extensive property in this? What will be the V value?
B is equal to
Extensive property. If we are taking a mass, then definitely B, what we are taking? You can tell me.
so B is equal to M when we are taking.
Yes, fantastic. B equal to M, and then if we are trying to focus on computing small this beta is only capital dB by what?
DM.
Yes, dm. Then it will be defining an intensive property, right? And this dm by dm, it will be coming what? It will be coming a 1, right?
Yeah.
And then
Yeah.
you can remember that when this one more thing is there, that we have to compute what, in left hand side, we have to compute the value of d capital B upon dt, right? Okay, so what question is asking? You can see there, the left hand side, it is asking about left hand side parameter, the value of left hand side. So left hand side value will be dB by dt only, right? You can see the this equation, you can see. I'm just erasing this. You can see here. Ashish?
Yeah, I can see.
You can see here. Wait a minute. So this one, dB by dt, we want this value. Got it? And this beta value we have already calculated. Beta value is coming 1. But still we want to calculate dB by dt. So here if we are taking m value, so it will be dm by dt, right? And you know that m will always be constant. Assumption, we do you remember the assumption?
There is no change in mass. Whatever is entering is getting out.
Yes, fantastic, good one. So dm by dt will always be equal to 0. Differentiation will be 0. Yes, so now you can get the answer that it will be only this one, right? 0. Good or not?
Yeah, I got it.
You can see the explanation here all again. Like they have calculated beta equal to 1. Then again, by the law of conservation of mass, we know that mass can't be lost. So definitely it is getting constant. So dm by dt will getting a value equivalent to 0, right?
Yeah,
And
yeah.
now you can see the surprising thing that just I mentioned. So I guess someone is getting inside this. Let me see. Okay. So Ashish, you can see the results that whatever the things are we are deriving, it is finally giving us a continuity equation. Can you say the name of this continuity equation? It is an unsteady flow continuity equation, right? Why is it unsteady flow? Because it is changing with the time. Okay,
Okay.
it is changing with the time. If I choose that storage is not changing with the time, it is getting constant. So you can see that finally ds by dt, again it is the differentiation of this, it is getting again a value of 0. And once it is getting 0, we can see that whatever the inflow it is coming, it is finally getting as an outflow, right?
Mhm.
So this is the result of this. Whatever the RTT theorem we are applying, and we are taking M as an extensive property, and then finally we are getting the conservation of mass like this, and we are getting the continuity equation. This is for the steady flow.
Steady flow.
This is for steady flow continuity equation. Okay. Okay, I'm moving ahead. Now again the next question coming is, read it properly again. Left hand side of the RTT, this one, for the momentum conservation principle is, it is asking. So now again you have to notice the one thing, that momentum conservation it is asking again. So can
Net
you
force,
solve
net
it?
force,
What?
net force.
Yes, fantastic, good one. Yeah, it will be a net force only. Net force. How you are getting this? Can you tell me?
Because dB by dt.
Yes, we have to compute this dV by dt. We have to compute. So what B
uh,
value you are taking?
dB by dt is equal to mass into velocity.
Uh,
Momentum, if we talk about momentum, then
yes.
this is
So
dB.
B value. What B value you are taking? That will be M into V, right?
Yes, m into v, mass into
Yes.
velocity.
Okay, fantastic. So it will be d m into V upon d into t. Now you know that m is constant, so it will be dV by dt.
dt.
Ultimately it is getting it
Um,
is giving us net force only,
force.
based on the law of conservation of momentum. Okay, Newton's second law, do you remember this? Newton's second law, it is saying that net force acting on a body, it will be equivalent to rate of change of momentum.
Momentum.
Yes, so it will be coming at summation of f. Now you can see again, you can see it, that yes, B it is taking mv, then again we are getting a beta value of v, but it is of having no use right now because we are concerned with the left hand side. Now based on the Newton's second law, we can see that this time rate of change of momentum is equal to the net force applied in a particular direction. So we are getting the summation, this one, net force. Now coming to the next question, can you answer this? Land that drain all streams and rainfall to a common outlet point is known as?
And the train or stream.
I want to know other person also what he is replying. Let me see. Okay, fantastic, good. Bala Murugan, you are replying, fantastic, nice to see you. Good, keep on. I think Bala Murugan, you have to see other points also, like apart from the catchment, there are there may be other points also.
Watershed, I think watershed is the answer.
Watershed is the answer, good one. Anything else? Because it is not a single answer, it may be having more than one also. Okay, I'm moving ahead. I will just describe you. Uh, so look at this picture. So I want to know, Ashish, can you tell me that from this picture what can you see? Like you have to describe it, like you have to briefly explain what are the things you are looking into this picture.
Yeah, we can see the tributaries
Okay, fantastic.
and the catchment.
Yes, you okay, you are you able to see this plants and all, and what is the like
Yes, sir.
you can see the tributaries, yes, it is good. Then again it is having a main channel also. Okay, when the tributaries are joining, you know, it is forming a main channel. So this is the
Mhm.
main channel, it is passing like this, okay, right?
Mhm.
Now can you have an idea something like the about this point, about the difference of this point, like one point is this and another point you are having like this one here. Can you tell the difference between these points, like in terms of elevation? Can you tell me?
Yeah, this is the land which is having the what we call lower elevation will become the catchment of that area.
Not the catchment, it will be an outlet. How much?
Outlet.
Yes, like firstly you have to see that one important thing is that this uppermost point is having higher elevation, right? It is having higher elevation, like in
Mhm.
the second picture also you can see. Okay, this one, it is also having some higher elevation. So here whenever the precipitation fall, the flow will take place in dormant way, dominating way. Suddenly the
Mhm.
water will flow away. Okay, so whenever the water it is falling, it is basically flowing through any kind of hill, it is making a boundary. It is start making a boundary. Okay, wait. It will start making a boundary. So you can see there will be a one boundary where flow will be generated and it will ultimately come and meet this point, meet to the main river. Got it? So this entire area is always called a catchment.
Mhm.
Like whatever the water which is falling in that area, it is getting accumulated and it is getting concentrated at a single point. At a single point means this point.
Mhm.
This entire area it will be called as catchment. It will be called as this one. Wait a minute. It will be called as catchment. It will also be called as watershed. It will also be called as basin. Okay. Okay.
Mhm.
One important thing I want to mention, that there will be a there will be one more option. And you can see that watershed boundary. Sorry. So this outer boundary of the catchment, or maybe a catchment, watershed, or maybe a basin, it will be called as watershed boundary, because these boundaries will be having a varying elevation.
Mhm.
Huh? They are the major water contributor, like major water draining points. Okay, from where the water will start flowing and getting concentrated at a point, right?
Mhm.
Got it? So this is the basic terminology. And one more thing you have to note out down, that where all the water, where all the water is getting accumulated, like I can draw one watershed, this one. Okay, and if it is having a main river like this, and there are certain tributaries are joining, so this what we call this point as? Any idea? This will be called as outlet. What? This will be called as outlet. And most of the time, do you know the fact that this, based on the idea of outlet, or maybe a location where we are getting that yes, maximum amount of water is basically getting accumulated at this point, this stream flow or maybe a discharge flow stations are basically we used to locate here, where the like you may be knowing that CWC discharge gauging station. Do you know this particular CWC station?
No.
Any idea? Have you heard of CWC?
Yes, yes, we heard.
Okay, so this is Central Water Commission, which is basically associated for providing the water related data. So
Hmm.
basically they are measuring the discharge data in India, in Indian river basin. Okay,
Hmm.
can you tell me one more thing, that from where we can get the rainfall data?
We can get rainfall data from IMD department.
Fantastic, good one. So meteorological data we can get it from IMD.
Hmm.
Okay, and also groundwater. Can you tell me groundwater source agency? So groundwater, for groundwater there will be two things. Either it will be associated to the water quality. So definitely water quality will be given by some other agency. So there is CPCB. You might be knowing this agency, CPCB. Then
Central
they,
Pollution Control Board.
yes, they are providing water quality related data. Then again CGWB, Central Groundwater Board, they are providing groundwater information, right?
Hmm.
As the like our discussion will go on, we will keep discussing on the data dissemination agencies, so that you will be more having exposure for those data also, that whatever the we are studying, it should be relevant, it should be significant to our ourself also, so that we can process these data for our major understanding. Now the next question comes, is that in controlled volume or Eulerian approach, what could be the possible options will take place? Can you answer?
In control volume or
So it is asking about controlled volume.
the
That is
control
a Eulerian
volume.
approach.
Mass.
Keep in
The
mind that yes,
mass transfer can take place across the control volume.
fantastic, mass transfer can take place across the control volume, that is good one. But still the thing is like multi options can be there, so you have to see again. Okay, because whatever the things are there, it has been already taught in the lectures, so based on that only the questions have been taken. So Eurasian approach, if you are talking, so definitely it will be having a control volume, and when the controlled volume is taking place, then definitely boundary, it will be a constant only, it will be fixed only. Space will be it will be specified.
Okay.
We should be knowing that yes, these rigid boundary are not going to change, it will remain same as it is. And then again one more thing, that particle phase as a continuum will be taking place. We are considering a continuous movement of the particles in this control volume, they are not getting lost. Okay, and then again mass transfer can take place across a control volume.
Hmm.
So this is the explanation, control volume, fixed region in the space, then Eulerian method treat the particle phase as continuum, then the mass is constant and can transfer across the control volume, and then whatever the fundamental laws that are there, okay, in the RTT it can be implemented. Now the next approach, that is a Lagrangian approach, that is related to the controlled mass, or we can say it as a system. So Ashish, can you
Let me the control mass. Particle are discrete. First, second is correct.
Good one. Good.
Uh, Fixed mass within the boundary.
Yes. Good. Mass will be fixed only.
Then mass transfer is not allowed.
Yes. Mass will not be allowed to transfer. Yes, of course. Because we are considering the control mass now. We are not saying that mass will be transferred to other form of energy. So this is the case. So yes, in our explanation we can see that for controlled mass or system Lagrangian approach, a system is a collection of matter having fixed identity. So here what is we saying, a fixed mass within a boundary. Then again it is considering a particle as a discrete. Yes, and then no mass transfer across the system boundary. Okay, these are already maybe in the course you might have seen these slides. Okay, so they are basically associated to the processes that have been used in deriving the Reynold Transport Theorem, and which is having a significance in understanding the conservation principles, mainly momentum, continuity equation, energy conservation. Okay. Okay, Balamurugan, you have okay, fantastic. You have replied in an almost, I guess, all the things you have replied. Fantastic. Balamurugan, can you introduce yourself before we will be leaving this session? Write in few words. That will be fantastic. So Ashish, have you how many assignments you have submitted yet?
I have submitted only one assignment as of now.
Okay, okay, fantastic. I'm a teacher in Anna University, Chennai. Okay, fantastic. Good. Nice to know you. Fantastic. Because in this session I'm having only two students, so definitely I should know both of you.
Okay.
Good.
Yes, yes, yes. You could please share your email ID and contact number so that we can, if we
Yeah,
have any query,
fantastic.
we
I
can.
will share you this one email ID. I'm just typing here. Thank you, Balamurugan. Thank you so much.
Yes, me too.
Yeah, we will be meeting in the next week again. Maybe it will be more interacting also because we will be learning more concepts. Uh, Definitely, we will be discussing uh, on the topic how we are getting the data, because in my terms, after understanding the fundamentals, we are going to work on the data only, whatever the data
Hmm.
we have, and ultimately we can understand the entire water cycle, that how these water hydro this one hydrological processes are basically varying, and they are varying with the space as well as the time. That is also one important thing. So we will be discussing as the lecture progresses on. Okay,
Hmm.
fantastic. Thank you for joining this session.
Yeah, thank you very much.
Okay, yeah, thank you. I'm stop presenting this.
Okay, bye.
Okay, bye.